halfway through the week and more than halfway through chapter 7. So what I'd like to do this morning is do at least 2 examples, and then we'll see if there's any questions so far. So the first example I want to do here is, you should be able to see here up on your screens. We introduce a concept, not sure if it was a full introduction, but of a point voltage source. And that's done in a lot of schematics to save on space. And what you have to realize is that what's actually here, what this represents, is the fact that there is indeed a battery. They're both positive voltage sources, so the batteries are with the positive side up. I'll show them like this, 24 volts. So if you see a point source and you struggle with it, draw the batteries. They're actually there. And they're quite often left out just to save space. I like to immediately show the plus and the minus. That helps me analyze the circuit, and I recommend you do the same. A battery or voltage source or power supply is of absolutely no use unless we connect both sides of it. And it's understood, unless stated otherwise or shown otherwise, it's understood when given a point source like this, that the other side of the power supply goes to circuit common. Right? The other side of this power supply goes to circuit common. And circuit common is simply a place that we call 0 volts. We do all our math assuming that as our starting point. Even though it may not be 0 volts, again, you may be flying up in space, you may be on a boat, you could be anywhere, but it's the place that we call 0, circuit common. Most circuits you're going to see show it on the bottom, but that's not necessary. It could be elsewhere. Something else that we must do is ensure that we know that if there are multiple circuit commons, realize that they are connected. Again, to save space, quite often the person who has drawn the schematic will not show a wire, but there is a wire here. There is a connection right there. They are connected. When you come in January and we work in the lab, you will be required to place a wire there or it won't work. We need to physically connect those points together. And all along here is indeed 0 volts along that wire. We have some music playing and we have a question. So Joe, is it Jose or Joe's? I'm always forget.
Jose.
Jose, okay.
Jose is okay too.
Okay.
Ray, how did you know the positive and negative sign for the batteries?
Because it's provided as a plus here, right? So if this had been -9, then we would have flipped the battery upside down, but it's a +9. So right here, just because there is no negative shown, it's a positive. And so we must connect the positive of the battery to that point.
Okay, thank you.
Okay, you're welcome. So we've got the concept of a point source. So this is called a point source. And it's done to save space so we don't have to show the battery or the power supply. But in actual fact, there really is a power supply there. So at first, until you get familiar with this, I would recommend drawing the power supply. That's one concept. The other concept is when we have multiple commons, we must connect them all together because that's the intent. Commons are all connected together. So that's another concept. And another concept is the concept of electrical points. So if I change my color here a little bit, maybe I'll use green for ground. This is all the same point. It is ground, 0 volts. Over here, this is all the same point because there's no components in between, no resistors, nothing in between. These are all the same point, and of course it's 24 volts. And over here, bear with me a little bit here. These are all the same point electrically. And so that tells us that right here, VC equals 9 volts. Right? I mean, we knew that already. It's labeled there. So if the question was how many electrical points are there in the circuit, let me get some different colors here. I don't know if this one will show up, but show up a little bit. Yeah. So here's an electrical point, point A. And I think our final point, I'll just use purple, is right here. So as far as electrical points in the circuit, we have 1, 2, 3, 4, 5. 5 electrical points in this circuit, all at different voltages with respect to common or with respect to ground. 5 electrical points. We have labeled 3 of these points, A, B, and C. The others are not labeled. We could label them if we wanted to. And our job here today is to figure out VA, VB, VC, and let's just pick VCA. This is a typical test question. Our test coming up in a little less than 2 weeks. We have a test. This is a typical test question. We already answered VC, 9 volts. We got one done. To find the others, I suspect I first need to find my current. This, even though we're in chapter 7, series parallel, do we see any parallel components here? No parallel. Nice, easy series circuit. The only trick is there are 2 supplies. So we do have a series circuit. We've established that. But we have 2 power supplies or batteries. Thus, we must figure out, are they series aiding or opposing? So to do that, that's why it's important to put the pluses there. The 24 volt one is going to try and push current in this direction. The 9 will push current in this direction. Thus, they must be opposing because they're fighting. One of them had been reversed, they would be series aiding. They are opposing, and this is a case where the bigger one always wins. 24 bigger than 9. So So current will be flowing in this direction. So we've now established the direction for the flow of current. Note that current does not care about commons. If we did not show this wire, then some textbooks, some instructors will say current enters this common and then comes out of this common. And there's actually a wire there. It's flowing through the wire, but if you don't show the wire, you can kind of picture current entering one common and leaving the other. I don't like that concept. It's I guess
a lot
correct,
of hidden wires.
But there's hidden wires. There's a wire there. Now, if it's automotive, it could be the frame of the car. If it's an airplane, it could be the frame of the airplane. Same on a boat, but picture it as a wire. There's rare cases where it could actually be flowing through the earth ground, but that's not normal, not usual. So picture a wire there. There is a wire. So what now we've established the current, the direction of the current, which is going from left to right. So now that we have established the direction of the current, we must, I know the upcoming test, half of you will not do this in the test. Historically, about half of you. There's 52 of you. I bet you 25 of you will not do this. So I challenge you to do it. Show current enters a plus, leaves the minus of this resistor. Enters plus, leaves minus. It causes a drop. And we must show this. If you don't show this, you will get in trouble with more complicated circuits. And then the current carries on. So this is VR1, VR2, VR3. The volt drop across a resistor has two pieces of information. One is the magnitude, how much voltage. The other is the direction of the drop. So by putting the plus minus there, I'm answering half the question already. Now the second part of the question is to get the magnitude. To get that magnitude, I need I. Once I have I will just use V equals IR to find each one. So I need to find I. So to find I need V over R. And here's the tricky part. It can be any V for a certain R or any V for a combination of R's. And I do not know the V, the voltage drop across each resistor. That's what I'm looking for. What I do know, if I treat all of these resistors as one big series resistor, I do know the drop across this great big equivalent resistor here. So when you do that, you can call it an equivalent resistance. In a series circuit, you can, with one supply, you can even call it the total resistance. To be safe, I'm going to call it the equivalent and circle it. And hopefully you can all see that there's 3 kilo ohms here. 1K, 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 and the total drop, just showing it this way, the total drop is how much?
15.
15. So we're dropping from 24, we're dropping to 9. So 24 minus 9, we have a 15 volt drop. So we could show this here as 24 volts minus 9 volts divided by 1K plus 1K plus 1K. So we end up with 15 volts divided by 3K. giving us
5 milliamps.
5 milliamps. So now we know the current here is going to be 5 milliamps. 5 milliamps here. 5 milliamps. So the 5 milliamps, when it runs through a 1K resistor, causes a drop of 5 volts. So we can find VR1 equals 5 milliamps times R1, which happens to be 1K, and we'll see that VR2 and VR3 are all the same because they all have a 1K resistor. They're all equal to 1K, so we're going to get the same answer for each one, 5 volts. So we have a 5 volt drop, 5 volt drop, and a 5 volt drop. So now, why did we do all this? We want to find the volt drop from A to ground. So the volt drop from A to ground, I'm getting a little messy maybe. Let's change our ink here a little bit. Anybody hazard a guess here? It's a volt drop. How much higher is A than ground? So if you want to know how much higher a point is than ground, or common, start at common and travel to that point. And you can travel to that point. You have a choice. We can go this way or this way, and we should end up with the same answer. So I'm going to travel this way, and then I'll verify the other way. So if I travel this way, my starting point is 0, and then I'm going to go up 24 volts. So that's up 24 volts. And then once I'm over here, I'm going plus to minus, I'm going down 5 volts.
19 volts.
And so we'll end up with 19 volts. So VA is 19 volts here. That's how much higher A is than ground. And I'll just keep traveling here to get VB. How much higher is B than ground? I could, instead of redoing all this, I could start at 19. That'll be my starting point. And then looks like plus to minus, I'm drop another 5 volts. So we're now at 14 volts. And then if we want VC, we can start at 14 and drop another 5 volts, that brings us to 9 volts. And going the other way, I could start at 0. And I go up 9. That puts us here at 9 volts for VC. And then going the opposite direction, I'm going up 5. So 9, go up 5. This is indeed 14 volts. So especially if I'm doing a test and I have lots of time, I might as well go both directions just to make sure I haven't made a mistake. If you've made a mistake, it'll show up very quickly when you try doing this, going in both directions. Any questions so far? We have our final question then is VCA. You're writing a test, you panic, don't know what to do. You should have this in your formula sheet. When I took this course many years ago, I make one piece of paper and I try to put all my formulas there. And then the instructor may or may not allow you to use it, but it's like a security blanket. The textbook is too big. I need one piece of paper that has kind of the formulas in there so I can remember them. And one formula I might want to put in there is that VCA is VC minus VA. VXY is VX minus VY. It's the first one minus the second one. Kind of out of space, I'm going to put it up. Whoops. Put it up here. VCA is VC minus VA. So I've done all this work already. I know VC is 9 volts, and I know VA is 19. If you're doing a test and you've got a mess like I have here, put little squares around to show, section it off so you don't make mistakes. 9 minus 19. What's 9 minus 19?
Minus 10.
Minus 10.
Minus 10. So we have 9 volts. 9 volts, and we want to go down 19. And yeah, that gives us minus 10. Minus 10 volts. So VCA is minus 10 volts. VCA, what is that VCA? Darn. So I have a meter, and I'm going to put one wire on C, and I'm going to put the other wire on A. And what I did in this case is I put the plus on C and the minus on A, and then my multimeter reads minus 10 volts, and it reads that because the meter is saying, you put the wires in you reverse the wires, basically. You put the plus to the point that you think is more positive, but 9 is not more positive. 9 is actually more negative. So the meter says minus. You're saying how much more positive is C than A? Well, A is actually more positive, so your answer has a negative in front of it. Question?
I have a silly question. Your figure, you keep putting it in your drawing, but you never introduced us. What's his name?
His name? Oh, gosh. Oh, I guess I can't give you his name.
Yeah, this drawing gets confused. It's
EET.
Sometimes a challenge. ET?
EET.
Yeah.
Yeah. Oh, I hit the wrong button here, but yeah, EET has disappeared.
The drawing is completely different from this original circuit. There are some on the assignment that seems a bit tricky for finding the total resistance with those.
So if you're asked for total resistance, there will not be 2 power supplies, I hope. Well, always 1 power supply, because total resistance is from the point of view of something, and usually it's just from the power supply, the 1 power supply. Okay, how come? Try this again. Pointer options. No, first I have to select pen, maybe.
So we cannot call this one total resistance? This R1, R2, R3?
I guess in this case we could. There are other circuits with 2 power supplies that we cannot. If you say total resistance, it's from the point of view of something, and in this particular case, when this power supply V1 looks Yeah, it sees 3K, and this one I think will also see 3K, but to be completely correct, when V1 looks to the right, it sees 3 1K resistors and a 9-volt battery. If the 9-volt battery has any internal resistance, that must be added. When the 9-volt battery looks, it sees 3K plus the resistance of the other battery, and that must be added. So they don't see the same thing. And if they don't see the same thing, I wouldn't call it total resistance. So what I would do is say that there is an R equivalent, which we're doing by combining R1 in series with R2, series with R3, and that is indeed 3K. As the circuits get a bit more complicated in Chapter 8, we will see that we'll have to avoid the use of the word total. The total resistance, like voltage is between 2 points, total resistance is also between 2 points, and we have to specify those 2 points. I don't know if that helps.
Okay, thanks.
So here we see that if this is 24 volts and point C here is 9 volts, then in between the two, from this point, to this point, that's a negative, is from 24 to 9 is 15 volts. So from 24 volts, 0 volts, 9 volts. So the difference between 24 and 9 is 15 volts. And that 15 volts is dropped across total resistance here. Total, I said it, total of 3K. And so that gives us our current as 15 volts divided by 3K equals 5 milliamps. And we're doing all this without redrawing the batteries and adding the commons. And so if we have 5 milliamps flowing through a 1K resistor, that's a 5-volt drop. The 5 milliamps here flowing through a 1K resistor is another 5-volt drop and another 5-volt drop. We do a quick check with the math. 5 plus 5 plus 5 is indeed the 15 volts that's dropped there. And so that works out. So now it's a matter of figuring out what is this voltage with respect to ground. And we start somewhere. If I start, I'll start at 9. If I start at 9, then I go up by 5, and then I go up another 5. So this must be 9, whoops, that should be 9 plus 10, which is 19 volts. And then this point is going to be 9 plus 5, which is 14 volts. If you prefer coming from the other side, we would start at 24, drop 5, 24 drop 5 is 19, drop another 5, we get 14, drop another 5, and we're back to 9. And so once you get comfortable with this, you don't have to draw the power supplies and the commons. Takes a lot of work and a lot of practice, and that's why you have a fairly chunky assignment there to maybe they force you to practice.
I haven't seen much example in this slide for the number 4 in the assignment.
No, we haven't done that at all. We'll get there. Number 4. Let me, this is the example we started yesterday. Just in case, oops. Because it's you, Matthew, I'm going to have a look at number 4 here real quick. And I'll see if I can tackle that at the same time. Whoops. There we go. Since it is an early number, sometimes we do things a little bit out of order, and you might have to skip a number as you do the assignment and get back to it after. Number 4 is rearranging circuits. So we're going to do a little bit of that right now. and maybe I'll finish up with having a closer look at number 4.
I was trying to play with multisim to rearrange, but still,
yeah,
it's still challenging.
Yep. Oh yeah. So we are going to look at doing that here. So let's do a little bit of rearrangement here. We started last class kind of looking at this a little bit, how we can take this whole arrangement and rotate it. Pretend this is a hinge and you're rotating everything down. So we should be able to move all this down so that you end up with your 5 ohms over here, you know, and get rid of it there. This 18 volts, we know that's a battery. So I'm going to bring it over here. That's my 18 volt battery. And the other side of the battery is going to ground. And then this -6 volts is actually an upside down battery, giving you the -6, and that's going to ground. And as we kind of straighten things out a little bit, I'm going to redraw the 18 volt battery here. I'm going to redraw my upside down 6 volt battery. Whoops. 6 volt battery here. They're both connected to ground. So I've got space. I'm going to show the wire that connects them. There's a wire connecting all these points. Ooh, and it looks like I have 2 other connections to that ground. I'm just going to put them there. I've got this connection and this connection. 2 other connections to ground besides the -6 volts and the 18. And what I like to do, well, I like to draw all the resistors up and down. I'll see if I can do that here. The 18 actually goes to a 6 ohm resistor. And then it goes to point A. That's your point A. And coming out of point A, we have a 7 and a 5 going to ground. We have a 7 and a 5 going to ground. And then we also have a 6 going straight to ground. And just to double check, using different color ink. Yeah, I'll show them in green. We have, yeah, that didn't work. Try that again. Pointer options, pen. Pointer options, ink color, wire. There. So we have this right here going to the 6, and this one is going to a 5. So I think I'm okay there. It's getting a little tricky, and I'm missing a wire. The wire I'm missing is this wire coming from the negative of the 6. The negative of the 6. Where are we going? We are going, oh, to point A. Point A. So point A is all of this. Everything in purple is point A. That's all point A. I can connect anywhere in point A. That makes sense. So I'll redraw the circuit. Did that make life easier for me? Because the original circuit was pretty challenging. Does anything stick out? Well, can anybody see anything in series or in parallel? Or any voltage across a resistor?
7 and 5 is in series. Everything else is in parallel to that.
Okay, so let's get rid of that 7 and 5, and I'll make this a 12. Hopefully everybody's okay with that. That simplifies it a little bit. 7 plus 5 is 12. What's in series and what's in parallel? Well, I guess the 12 and the 6 are indeed in parallel. But I've come to a point where I've done enough of these that I don't know how much that's going to help me right now. I find it easier if you are given the voltage across a resistor. I mean, we have all kinds of tools now. We've got current divider, voltage divider, all this stuff, but I always come back to, if I know V and R, I want to figure out the I. And that 6 volts is applied directly across that 6 ohm resistor. So there is 6 volts across that 6 ohms. So, oops, current enters a plus, leaves a minus. So, of course, current leaves a plus. So the current flowing through that 6 ohm resistor right here, that's got to be 1 amp. So I can find IR4 because I know VR4 and I know R4. I just figured out that the plus and minus of the 6 volt battery is connected directly across each side of the 6 ohm resistor. So I have 6 volts across 6 ohms giving me 1 amp. And at the same time, what I just figured out here is that that same 6 volts, because as you mentioned earlier, they're in parallel, the top and bottom of the 6 ohm resistor is connected to the top and bottom of the 12 ohm resistor. That's the definition of parallel. Parallel resistors have the same voltage. So I now know the voltage across a 12 ohm is 6 volts. So I can find the current through the 12 ohm resistor to be 6 volts divided by 12 ohms, and that's 0.5 amps. So I go back to my original drawing. I don't have a 12 ohm resistor. But the 12 ohm resistor, when we rotated that branch kind of down, and here is my 12 ohm resistor, and the current flowing through it looks like it's going up from ground, from common, is 0.5 amps. So this must be 0.5 amps all the way into here, 0.5 amps. And this one's 1 amp. Ooh. So node A has 4 branches. If I look at node A with a little bit less clutter, I have current here through the 6 ohm resistor. I have a current here through this 6 ohm resistor, which is R4, and a current over here from the 7 ohm resistor. And we just figured out that's 0.5 amps. This one is 1 amp. Oh, we got another one here going to the negative 6 volt battery. So So I just need one more current and I'm pretty well solved. I got to find another current.
Yeah, you're 18 volt over 6 ohm.
Is 18 is V1. So, okay, I think what you're telling me is to figure out V1. Figure out what is a volt drop across the 6 ohm. So I can figure out IR1, which is this guy, IR1, if I knew VR1 and R1. Of course, I know R1, it's 6 ohms. I just need to know VR1, which the schematic people have conveniently for us kind of labeled it V1, but I prefer calling it VR1. We just need to find that voltage. To find a volt drop across a component, what we must do, pardon me while I change the ink color. Let's go to a red. We must find the voltage on one side, voltage on the other side, and subtract the two. That is the drop across VR1. So VR1, well, I know the voltage on this side, it's provided right here. So that's 18 volts. So VR1 is going to be 18 volts minus whatever voltage this is. It happens to be the voltage at point A. That's
-6.
So 18 volts minus over 6 ohms. And you're telling me that is, it's the same point. Look at that. So that must be -6. Watch your double negatives.
24 volts over 6 ohms.
24 volts over 6 ohms. Giving us
4 amps. Now your I total.
There is no total, but we can find out what we've labeled here is I of the 6 volt battery. So we've labeled this guy just simply I. So what's it going to be?
4 plus 1, 5.5 amps.
5.5. So why are you adding them? Why are you not subtracting any?
Because they're all pushing in the same direction towards your -6 volts.
Yeah, so Kirchhoff's current law says the sum of currents entering equals the sum of currents leaving. There's only one that's leaving, that's this I, all the others are entering, so it's going to be 5.5 amps.
So can we still call it your current source?
Well, there's two sources there.
Yeah, because there's two sources, okay.
Well, we could call it source 1, and the 18 volts, I guess, is source 2. Wow, this becomes a messy circuit. I'm going to memorize these values. 4.5 and 1. 4.5 and 1. Oh, I got it worked out anyway. Slideshow from current slide. So we had 4 amps, 0.5 amps, 1 amp, and this one was 5 amps. Oh, that looks cleaner. That looks neater there. I don't even remember why I wanted to do this. In a circuit like this, if somebody said, you know, what's our total? Yeah, you shouldn't be asked that question. There's equivalent resistors as you combine them, and it depends on the point of view. We can redraw that circuit as we did, and it's a little bit neater here, and then we should be able to see here the 4 amps, 0.5 amps, 1 amp, and here's our 5.5 amps being hauled in by this vacuum, that is the minus, and then pushed out of the plus. And then we have 1 amp. Oops. This must be 4.5 amps. This is 4 amps, so this must be 0.5 amps. And here's our point A. Interestingly enough, point A is at -6 volts because of our upside down battery. Our right side up battery places here 18 volts, giving us a drop across this 6 ohm resistor of 24 volts. So we have an 18 volt battery, a 6 volt, yet a 24 volt drop, which is bigger than both of them. And we can achieve that by flipping one of the batteries. And that's not magic. It's, I keep referring to this number line. I need it to maintain my sanity. I've got 18 volts as E2. I know there's going to be a 0 somewhere because that's my happy place, my safe place. If I panic, I know there's 0 volts there. Always know that. And I reference everything from that 0. The 18 volts, of course, is 18 volts higher than 0. And over here at this point, the -6, it's actually down here, -6 volts. And the way I can get the 24 volt drop over here is going from +18 to -6. There's a drop of 24, giving us our 4 amps. Any questions? Yes, Louis.
Hi, sir. For V2, because it's indicated there that it's a positive and negative V2, and it's parallel to a -6 volts power source, will the answer be +6 volts?
Ah, good. So we didn't do V2. How come I lost my pointer? Pen. Yeah. So how much V2, because it puts the positive there, it's asking how much more positive is this point than this point? And what I'm going to do, I'm going to call it VXY. And the first one is the positive, second one the minus. So I'm going to call this point X, and this is point Y. So VXY by definition is VX minus VY. And VX in this case is -6 volts. And so we have -6 volts minus, and VY is, well, it's right here at 0 volts. And So we end up with -6 minus 0, or -6 volts. So with the plus up there, we take the whatever voltage is given. It's the -6. We can overthink this. This is one that's really easy to think too much about, but I'll show it two different ways here. This R4 we could show the volt drop across R4 as 6 volts, or we can show it as -6 volts. We actually have -6 volts on one side, and we have 0 on the other. The 0 is the more positive, so if you show the polarity and you are correct in showing it, 0 is indeed more positive than -6. 0 is more positive than -6, and we show that as positive 6 volts. But if you put the minus here instead, I get reversed there, but let's revert. If I put the positive in the wrong place, because 0 volts is actually more positive than -6. And so if I put the positive in the wrong place, then I compensate for that by putting a negative there. So point X is -6 volts more positive than point Y. Point Y is 6 volts more positive than point X. So it's your frame of reference. I don't know if that helps any. We'll have to practice that a little bit more.
Yep, thank you, sir.
Yeah, I think I agree with you with this chapter being the hardest so far anyway.
Yeah, it's a challenge. Let me keep plugging through here. So when you download the PowerPoint, you'll get the answers up there, and I'm putting up, current to the right. So voltage, we need the polarity plus minus. Current, we need the direction. Which way is it going? If you follow along in the textbook, on purpose, I did it one way. The textbook redraws it a different way. So this example is in the textbook, and you'll see it done kind of a third different way. They put the 6 and the 18 next to each other, and you can have a look at it and see. So we just kind of to wrap this up a little bit. Here's my battery. I have two ways of identifying the voltage. If this happened to be a 6-volt battery, I could show it as 6 volts plus minus, or I could show it as -6 volts minus plus. Note that I'm showing the minus where it's obvious this is the positive. So it's not really a mistake, but it's showing it the wrong polarity. So I compensate for that by adding a minus in the front here. In the same way, here I know, where was it, that this was 1 amp flowing up. 1 amp flowing up causes a drop in this fashion. I know that current enters a plus, leaves a minus of a volt drop across a resistor. And I could show that as 6 volts. But if you showed it like this, you would be marked 100% correct as well. So when asking for V2, if the plus is shown where the minus actually is, then it's a minus 6 volts. If V2 had been asked like this, then it would be 6 volts. Matthew, problem number 4. You know what? Is it 4A that's causing you a problem?
Yeah, that one and B, because of the terminal ends or whatever.
Yeah. So let's have a look at that. Is anybody else having some concerns with that?
Right? Sorry.
Yes.
In there, point A is actually a line, right?
So a point physically is a point, but electrically a point can be many lines. So good catch here. Point A in this circuit, point A is everything in red here. Point A, when redrawn. So if the test said use a highlighter and highlight point A, you would have to highlight everything I just highlighted in red. So because remember, this is an electrical point A. Electrical point A. Okay, we just did a mute here. So that an electrical point can cover lines. So good point. Good, no point. No joke intended. Good point. Good point. An electrical point is at the same voltage, and there are no components in between. And the nice thing about an electrical point is we can move components all around this electrical point. For example, if you know, if I had this circuit, I can move as long as I don't cross any points. I can redraw it like this, where point X, these are the same circuit. Electrical points, we can pivot, move around, as long as we do not cross over any components. And what we're going to do to show that, we're going to look at 4A. And 4A has 2 terminals. We have 4 ohm, 4 ohm, 10 ohm. So we have, I should have given myself more space here. 4 ohm. 10 ohm.
So those white circle, point, whatever. Those are what we call electrical points.
Yes.
Okay.
Okay, so I think this is 4A. Was 4A. Now we come to the question, we're going to ask, what is our total? And if an instructor asks you, what is our total for this circuit? You would say, impossible to determine, because the R total is from a point of view. And when you come to the lab, you will be holding a multimeter and you will have 2 wires and you are measuring resistance and you want to know, where do I put the wires? Do I connect them one here, one there? Or maybe it's one here and one over there? Or maybe I'm going to put the red wire here and the black wire here, and I may get different values of resistance depending on where I put it. If the circuit had a power supply, then what you're going to do in the lab is disconnect the power supply and you'll put your meter there and you'll measure our total looking this way. So if there is no power supply, then your instructor, your textbook must tell you where to look. And in 4A, they say, look in over here. So what they're meaning is hook up to these 2 terminals. As we get to chapter 8 and chapter 9, this becomes important later because you might get a test that says connect to some strange terminals and it'll give you a different resistance. So here, a little easier, but thankfully they did this and they put these 2 extra terminals there just to trick you, just to make you think about it a little bit. So looking from this point of view, what happens when I hook up my multimeter is my meter sends a very small current through and measures a drop across, divides the 2, and it gets a total resistance. So here, I'm going to send a tiny current through, and the current splits up, and none of the current heads to those terminals. This is said to be an open circuit right here. It's an open circuit. So all of the current heads back, and they join back up, heads down, no current that way, and comes back. So those points are there just to trick me. So I'm going to redraw this circuit with my 4, and I want to call this point X. It's right there, but I'm not gonna show that. Those are opens, and right here, this comes down to my 10. And I'm not going to bother drawing that. There's no current flowing there, and there's no current flowing here, so I'm not showing those. And so I think it becomes apparent here that the 4 and the 4 are actually in parallel. I'm going to redraw that to show them. But what I'm going to do now is I'm going to take this point and I'm going to pivot everything down. And I'm going to show 4 and the 4 joining up here at point X, because I've rotated everything down. And then from point X, I've got my 10 heading back here. And so that becomes 2, point X, 10. what I find very helpful when I'm doing these, what helps me a lot, is to put a point that I can track as I'm doing them. Make sure I don't make a mistake, because I'm making sure that none of those components cross over that point. Any questions about 4A?
That makes a lot of sense.
I didn't trace it that way, but I got the same answer.
Yeah, there's going to be a lot of different ways of doing it. I've seen, maybe not, it won't be for the virtual class, but I've seen in-person classes in the past, in my 30 years there, have group sessions in the evening. They come and meet, and it was funny. They showed me they had rope and they had toilet paper rolls for the resistors, and they were sliding the toilet paper rolls on the rope and rearranging everything on the floor, you know, to rearrange the circuits to help them visualize what was going on. And that would be one way of doing it. You could build this with rope. I think it was Matthew who mentioned using multisim to do that. There is a free, because it's kind of obsolete now, a package called Circuit Maker that I use. It's not as powerful as multisim, but it's very, very quick. So what I've done in the past, like if I put a B battery, we had a resistor, a resistor view, and
It looks easier than multisim for some reason.
that's why I like to use this for, whoops. That was 0 for ground there. Options, pin dots. So I think this was our original circuit. Looks something like this. And you know, this looks a little confusing, but I can, with multisim, you can do the same. We can move these. So what I'm going to do here, what if we move this down and then rotate? It rotated the wrong way. Let's rotate again. There. Rotate, and then I can move that. Doesn't like it. There we go. It's an old package, so it and what were we doing here? Rotate 90. Rotate 90, rotate 90, bring it. So with multisim, you can do the same thing and kind of rearrange them until you still have to know a little bit what you're doing, but and you can see here, whoops, if I can grab that wire, there we go. And the net result is we're ending up with I think I lost some connections along the way here, but we end up with the resistors. These were 4 ohms, so
No, it's kind of cool because it lets you fix your puzzle without disconnecting anything.
Yes,
So
and
you know,
it prevents you from disconnecting, because one problem that we encounter is accidentally disconnecting and thus not following the rules of the circuit. Yeah, and so we didn't have the battery, but it was from that point of view. And so here we can see that we have 4 in parallel, 4 giving us 2 in series with 10 giving us our 12 ohms. I think it's a free download, or if you find it, Circuit Maker student version. Multisim is much more powerful and has the equipment. Matter of fact, the equipment in Multisim in many cases is the same equipment you will be using in January. So that's a good thing about Multisim. Maybe I'll do one more slide. We do have a class on Friday where we'll carry on, and also it is much better for the class if you guys, well, like Matthew did here, if you are working on the assignment and come up with some questions for me. Because I do have a lot of examples, but I will run out. And what we do usually in person is we'd give you some time to work on the assignment, and I can walk around and help you. That's very difficult to do here. But if you give me some questions you're stuck on, we can go through them together. And here we have what looks like a very complicated circuit. There's only one battery, so I don't have to worry about series aiding, series opposing, but I do see many resistors that could be in series or parallel. So I find the easy ones. I can see, and hopefully you can see, that R1, R2, and R3 are in series, R8 and R9 are in series, and so I can simply redraw. I'm taking R8 and R9, 3 and 6, and making it 9. So this resistor is not real. This is an equivalent resistance made up of the 3 and the 6. Same thing over here. And here we did something fancy. We called it R123 because we had R1, R2, and R3. So whatever works for you, find a way. It's going to get complicated. Find a way to maintain your sanity, to keep track of what you're doing. So I sometimes I'll just put R123, and that's 4 plus 8, that's 12 plus 12, that's 24K. So again, that is not a real resistor. That's not a real resistor. It's a combination of those 3. I'm representing them right there as I simplify the circuit so that I can solve it. And you do that until you solve it, and then you work your way back.
like sometimes some problem I'll just put like RT equal, and I'll kind of make my formula, but like just like one linear equation or whatever. But sometimes I find like I have to go step by step, showing like a little schematic because I'm crushing it into like an accordion.
So we're gonna bring it smaller and then bring it back out. Yeah. Find a way. Yeah. Good. So here I expanded it to show it kind of larger. Oops. And you know, that was our initially 2 resistors that we crushed. Once we do that, sometimes if your instructor is nice, sometimes it becomes easy. Well, 9 in parallel with 9. So I see this as 2 equal resistors. So this is 4.5 k ohms. And 24 in parallel with 24, well, that's 12 k ohms. And then that's going to be in series with this 12k. So I can look at this whole branch up there as being 24k. So that's 12 and the 12. And then over here, this branch is going to be 4.5 and 12, 16.5k, a little tougher, a little harder on the head, that one. And the 72 volts, you know, we've got 0 volts here, and we've got 72 volts here. And you know, the electrical point, that is 72 volts, is all along here. So everywhere along that point is 72, which means that there's 72 volts dropped across that 24k. So I can figure out this current. I'll call it I5. So I5 is going to be 72 volts divided by 24k, giving us 3 milliamps. I6 right here is going to be 72 volts divided by 16.5k, giving us 4 milliamps, if I'm doing that right. 30, no, it's not 4. Did I do this right? 4.5, 16.5, that's 33. My calculator. 72 divided by 16.5 equals 4.36. 4.36 milliamps. They combine. 3 and 4.36 gives us 7.36 milliamps. Because there's only one power supply, we can find our total. We can make up an equation for our total, or we can cheat and use Ohm's law. I'm going to take the lazy way out. Our total, if there's only one power supply, it's E divided by I total, which we've labeled IS this case. So we have 72 volts divided by 7.36 milliamps. (72) divided by 7.36 milliamps, and I'll have to add
9.78 kilo.
9.78 kilo ohms as our total. But I know you guys wouldn't be happy with that. We would find our total the long way. If I look at this side, I've got 24k in parallel with 24k. That's these guys. In series with 12k. That's this guy. When I do that, I end up with this big branch here. Oh, which I actually already know is 24k. And there is another big branch over here, and the top of that is connected to the top of that. The bottom is connected to the bottom, so they're in parallel. That's in parallel with 12k, which is this guy R6, in series with 9K, parallel 9K. But I already figured that out. That was 16.5K. Messy here. I'm gonna, where can I redraw that? I'm running out of space here. I'm gonna redraw that over here. Our total was 24K in parallel with 16.5K. So here's my 24K, 16.5K. They're in parallel. And when we work that out, 1 over 24K plus 1 over 16.5K, we will get 9.78K. So we get 2 different ways to find our total. It's probably another 3 or 4 different ways to find our total. Any questions? If you had this as a test question, how long would it take you to finish it? The answer is the more you practice doing the assignment, the quicker it'll be. Any questions?
Yeah, it's very straightforward, but sometimes you cannot see how to get one value. You don't realize how to get it.
Yeah.
That problem I have like a couple of times.
Yep. If I'm a big fan of Sherlock Holmes. You put on that Sherlock Holmes hat, and you're an investigator. You're looking to always see. You're always looking. Where do I know 2 out of 3? If you know 2 out of 3, you got it. Yeah. So, and somebody in the comments put number 37. Number 30. We'll wait a little bit on 37, but yeah, 37 is 3-dimensional. That becomes very tricky. I think we only have a few more slides to do, and I think I might have to wait to complete this one. We'll complete it on Friday, but I do want to start it right now. So we got about 5 more minutes, and then we'll give you a nice lunch break or a break. And a quick look at this strange 3 power supplies. Ouch. 3 power supplies. There are 2 different approaches for this type of circuit. One might be to redraw and keep redrawing until it makes sense to you. And redraw, I highly recommend if there is 1 power supply. If you have 1 power supply, then use colored pencils and redraw so that all the resistors are up and down, and we can redraw and maybe solve the circuit quite easily, or it would help with 1 power supply. With 2 power supplies, you might try to redraw, but sometimes you can get bogged down and it takes too long, and you're not getting anywhere. The second would be And is there anything real easy or obvious? So we look for anything obvious. And to do method 2, I always say start with what you know. I know that. Add anything else that you know. So I've already got VA because 0 go up by 20. This electrical point, which is A, is 20. Now, I think I'm going to pick this way because this is travel through circuit. Make sure you have 2 vaccines before traveling through the circuit. I'm traveling plus minus. I go down 5 volts, 20, go down 5. This must be 15. Uh-oh. I'm stuck. I cannot travel any further because I would need to know the I and the volt drop. I need to know this I to give me the volt drop. I don't know them. I'm stuck. Maybe I'll go back to my 20. Oh, I don't know this volt drop. I'm stuck. I'll go back to 0. I don't know the. Oh, I know the 8. I can go from 0. And I go minus to plus. I go up 0. I go up 8 volts. So VC must be 8 volts.
Run.
20.
Ray, run.
And 8.
Sorry.
What's the drop across the 10? 20 on one side, 8 on the other. Whoops. What's the drop across the 10?
12.
12 volt.
12 volts. And then here we have 15 on the one side and 8 on the other. So the drop across this one is
7.
7. And now we got 15 on one side because electrically this is all 1 point. 15 on one side, 0 on the other. So my drop here is 50. Too easy. This difficult problem becomes very easy when I do a little bit of travel through the circuit. I think I'm going to stop here. Any questions?
Yeah, the 20 volt, it goes up to VA. So it's just 20 volt. The 5 volt doesn't counter it because 20 is stronger.
When we look at currents, these batteries are all trying to supply current or be charged, and they will affect the current, but they will not affect voltages. Those power supplies are meant to provide a voltage. If I was to put a 20 volt battery and a 5 volt battery and asked you, what is this voltage? What would the answer be?
I guess you put, well, you put 20.
I'm going to stop you right here. It's just going to stop you. There is no answer. When we ask for this voltage is with respect to ground. We need a ground or a common. I did not show you one, so this is not a fair question. There is no solution. I must put a ground. Must put a common there. Now, if I put the ground or common here, the answer would be 20 volts. If I put the common here, the answer would be 5 volts. But they're both too easy. So what I'm going to do is put the common here, and I'm going to put, and I'll make it easy, I'll put a 1K resistor and a 1K resistor. Now, can anybody tell me what the voltage is? Because now we can answer it. We can only answer it if somebody provides a ground or a common and a full circuit. Now I can answer that. Who has the answer? What we're going to do is we're going to stop here, and on Friday we'll award $1 million to whoever can answer this. No, maybe not 1 million. Maybe when you come in January, we'll give you something. We'll leave it like this. 20. I'm going to lose it when I shut down. So I'm going to leave you guys for now. I'll see you tomorrow for computer interfacing. And then on Friday, Friday I have a few more slides for chapter 7, but we're going to solve this puzzle. And then hopefully somebody will have this. Okay? See you guys on Friday. Good luck with the puzzle.
See you. Thank you.
Yeah.
So, okay. Give you a second to write this down. It's the puzzle.